I'm here presenting some work that we've done this year on the relevance of UTP bedding modulus when measured on the geometric ballast plate. This work was performed by my colleagues in Belgium who weren't able to come today. And you'll see Scott Triple on the program. He was also unable to be here today. So here I am. Got this presentation on Monday, and I'll do my best to answer all the questions here. So first, we're going to go through a little bit of background on bedding modulus. Thanks to Brett and Eric's presentation, I'm not going to get too far into what under tie pads are supposed to do or anything like that, but we'll cover a little bit of the DIN, EN, and now ARIMA norms for measuring bedding modulus. We'll briefly touch on environmental aspects and the carbon footprint. We'll talk about some independent testing we had done at TU Munich and how the variation of these results compares with alternative materials. We'll talk a little bit about surface contact, which previous presentations have also touched on, as well as a brief case study. So under tie pad stiffness is most often measured using a geometric ballast plate, which was originally designed for the European norm and has now been adopted into ARIMA Committee 30. So when we measure bedding modulus here in the US, we're also using the same geometric ballast plate. What we have found through doing more and more testing with this plate, and as we've developed higher stiffness products, is that our products are not achieving the same high stiffness on the geometric ballast plate as we're measuring in track and on the older normalized ballast plate. So we have some independent test reports to back that up, and kind of just putting the question out there, are we measuring things in a way that's relevant to track performance, or are there other considerations? So to define bedding modulus, it's a linear stiffness per unit area. So it's expressed in pounds force per inches cubed, or in newtons per cubic millimeter. And pictured here is the normalized ballast plate, which was originally used for the DIN standard, which is basically a cast of some ballast stones. And a number of years back, the EN standard developed the geometric ballast plate, which was something intended to be a little bit more repeatable and is what you most often see used in labs. So if I talk about test block stiffness or GBP, I'm talking about this test that's pictured here. Before we get into the test data, just to talk a little bit about the environmental aspects, because I think it's especially our responsibility these days. Every mile of Pandrol under tie pads sequesters 600 ties worth of tires, 600 end-of-life tires. So because we're using a recycled product, we get the benefit of the natural rubber properties, but we also take the benefit of having a low carbon footprint. And something that I'm especially excited to share today is that for 2022, Pandrol's UTP production is carbon neutral, certified by an independent party, and we're financing green energy projects in India to offset our carbon footprint. So to get into the testing at TU Munich, we did some ballast box testing, which I think we've actually seen some very similar photos already today. And in this case, we were looking at our stiffest product, which is it's a 5.5 millimeter thick pad with very high density. And we had a 2-tie setup with, and we ran 2 million cycles for stabilization, and we measured the dynamic stiffness after those 2 million cycles. So we did this test with naked ties and then with the under tie pad to compare the results. So the key conclusions here is that with the under tie pad in a ballast box, we measured a dynamic stiffness of over 500 kilonewtons per millimeter. It's like, oh, okay, great. But when we take the dynamic bedding modulus that we measure on the geometric ballast plate, it shows us that we should have expected something more in the range of 250 kilonewtons per millimeter. So we're missing by like a factor of 2 there. And then we also observed a total deflection of the ballast and UTP system of 0.32 millimeters. And when we subtract the deflection from the naked tie, we're looking at 0.23 millimeters coming from the under tie pad alone. which again doesn't agree with what we would have expected from our testing on the GBP, which told us we should expect about 0.5 millimeter. So this is a way to visualize that same data. So the gray curve is the ballast deflection alone. The black is with the ballast and the under tie pad, and then the yellow is just the difference. So we're in a couple of slides, we're going to compare these curves to the curves that we get from the GBP test. So we took a closer look at track condition 3 in the European norm, which is equivalent to the heavy rail load condition in ARIMA chapter 30. And for reference, track condition 4 is kind of similar to the freight load environment that we have in chapter 30. And when we report the stiffness per ARIMA or the EN standard, we're looking at a working pressure of 0.1 megapascal. And what we found through our testing with TU Munich is that we should maybe be looking at a working pressure of 0.2 megapascals for this track loading condition. So it seems like maybe we're underestimating the load by a factor of 2 for our bedding modulus testing. We applied a back calculation to the other track loading conditions, and the trend that we generally saw is that there's better agreement for softer under tie pads, and the gap kind of widens as you start looking at stiffer and stiffer products. So here we have the black curve is the bedding modulus, the load deflection curve that we measured with the geometric ballast plate, and then the yellow curve is what we measured in the ballast box. So that's where we came up with our 1.68 correction factor. But the big thing that you're seeing here is nearly linear behavior on the geometric ballast plate, but you're seeing some nonlinear behavior in the ballast box. So you kind of think, what could be going on there? The support condition must be changing during the course of the test, which would be realistic. And here we have some tabulated data for the working point for each track condition in the European norm for 0.8 megapascals, 0.1 and 0.14, and then what the actual working point we found in track. So to compare with alternative materials and to kind of rewind back to the normalized ballast plate, we looked at TPU and the resin bonded rubber products. So when we changed from the normalized ballast plate to the geometric ballast plate, the stiff TPU products generally tended to increase in stiffness. So they started reporting higher bedding moduli, where the resin bonded rubber products from Pandrel and others became softer. And a good example here is for the stiffer products, where we had fairly close agreement between two competing products reporting similar bedding moduli. And then we changed the test method, and suddenly one has gotten stiffer, one has gotten softer. So we're seeing a deviation of close to 40% in that case. And here we have a plot from the EN working group that developed the geometric ballast plate. And on the x-axis, we have the bedding modulus for a given product using the normalized ballast plate. And on the y-axis, the same product on the GBP. So of course, ideally we'd have a linear fit there, which we kind of see for the soft and the intermediate stiffness products. But then as we get stiffer, again, the TPU and EVA products are appearing much more stiff on the GBP, and we're seeing some softening with the resin bonded rubber products. So, looking at the block testing versus the ballast box testing, the pad working area is the same. We can control for that. And then the next thing we looked at is the surface contact of the UTP. And that's kind of the obvious, aha moment. So we were estimating that we're getting a lot less contact area with the GBP than we get in a ballast box at similar loads. So in the ballast box, we tested 3 different stiffness products, and then we also ran the same products at different load points on the GBP. And we see that the softest product is all the way to the left, and you see kind of close agreement between the contact area. But then as you go to stiffer and stiffer products that weren't as popular, 10, 15 years ago, we're starting to see pretty large deviation in the contact areas. So, basically the geometric ballast plate appears to underestimate the contact area for very stiff products. And again, why did we come up with the GBP in the first place? Basically, we wanted repeatability and control so that multiple laboratories could test the same products and get the same results. So that's something that us in Committee 30 talk about quite a bit, and that was definitely a success. We also had the ability to test 2 sizes of specimens, which gave more flexibility for suppliers and for end users. So that was great, but it seems like we missed the mark with having representative surface contact for a wide variety of materials and stiffnesses. So again, we did further testing with the GBP and the normalized ballast plate for a few different products. And again, as we go with the stiffer products, we start seeing a bigger gap between the expected performance. So, what does this mean in track? We had an opportunity in Belgium to do some A/B testing, with and without under tie pads. So this area had poor soil quality. They had issues with track settlement and frequent tamping. And we measured some vertical track deflections under traffic of 2.2 millimeters. And then in similar areas with the under tie pad, we're measuring 2.4 millimeters. So in that case, we're seeing an actual deflection of 0.2 millimeters from the UTP. But when we look at the dynamic bedding modulus that we measure with the geometric ballast plate, it's telling us that we should be expecting something in the range of 1 millimeter and greater. And the other really important fact here that we see is that kind of regardless of what the numbers are, we do see a reduction in track settlement, and they increase their tamping frequency by a factor of 2. So they have to go out half as often. We have a number of conclusions here. I don't think I need to go bullet by bullet, but the big things here is, from these other presentations that I've seen today, I feel like the industry is on the right track for under tie pad application in North America. We're investigating the right things. We're seeing that maybe the bedding modulus is not the number to live and die by for expected product performance in track, but contact area plays an especially big role in that. So I'd like to thank my colleagues, Jamie and Thomas in Europe, that put together this presentation and did the testing. And I'm open for any questions that anyone might have. Marcus.
Yeah, and I know we talked briefly, and you might pass this question along, but regarding the work that we had done previously, categorizing the GBP, we agree that it's not representative, but one of the things we found, which seems contrary, is that the contact area from the GBP was actually greater than what you would get from most of the balance situations that we tried to come up with. I was curious if you could speak to that, or kind of what your idea is for any uniform testing.
Yeah, I think that's a good topic of discussion for the subcommittees, but I would ask what the stiffnesses of the UTPs that you were testing and what the product type was, because we saw big differences in soft versus stiff products, and then also from a resin bonded rubber versus plastics such as TPU and EVA. So everything doesn't always trend in the same direction. And something that we didn't look at all were extruded rubber products, which were totally excluded from our investigation to date. Hey, Bill.
John, did I understand you correctly? All of the pads that you tested were 5.5 millimeter pads?
What we tested in the ballast box at TU Munich was a 5.5 millimeter pad. For some of these other plots here, the plot on the left is a 7 millimeter pad. On the right is a 10 millimeter pad. But basically, the trend as we go to thinner and stiffer pads, we start seeing a divergence in the GBP bedding modulus and what we measure in track. Yes, Aldo.
How can you estimate the life cycle of the
that is a question I would have to pass on to my colleagues. For estimating the life cycle, that's something that's proven pretty difficult. But in Europe, we've done a lot of fatigue testing with the Vibragir testing. We have a long history of having these products installed with SNCF in France. And kind of the short answer is, for all of our customers, the under tie pad is lasting the life of the tie. And the big gains that they're seeing is in frequency of going out and doing track maintenance. Brett?
Would you have any recommendations for coming up with an alternative to the ballast plate that gives a result that's more realistic of what's in track?
It's not at this time, because I think, and maybe Winfried might be able to add something, but there was like a good reason why we got away from the normalized ballast plate and moved to the GBP. And I don't know if it could be like some kind of design of experiments to come up with different geometry, but something that gives us the closest correlation to what we actually measure and track is doing ballast box testing, which is really labor intensive and not repeatable to perform. So it's not practical. So I think Pandrol is open to looking at different test methods and would like to collaborate with the industry on that if we see a need for it. Great, thank you.
I'll ask one.
Oh, sure.
Did you look at any differences when you're using, for example, just flat plates? Do you see any difference in the way you're measuring between the different kind of moving products that's supposed to have kind of a similar stiffness under one condition, but if you throw them on just without the profile of a plate, do you see them kind of converging back?
That's not something that we've done yet, and that's a really interesting point, because we have done a lot of that type of work for rail pads, right? And then we find that the influence of the surface is pretty key. So we use emery cloth to kind of control that interaction between the surface and the pad and the plate. So I think that's a pretty interesting idea, something that we could look at as well.
Yeah, very, very interesting as we get into tomorrow. So